And the point I'm going to convey to you is that the X will part company with the ancestors of the duck-billed platypus. A little later, we'll part company with the ancestors of kangaroos, dogs, and... Okay, so we're going to focus on a set of chromosomes coming down here, and this set of chromosomes is eventually going to make it all the way down to man. And as it comes down here, we'll blow it up. We're going to focus in particular on this one autosomes. And just to simplify, throughout the rest of the animation, we'll just show one version of the X and the Y. Here is an ancestral gene which has now mutated on the proto-Y. This is the initiating event in sex chromosome evolution, an ancient ancestor which survives today on the Y chromosome. Now, how was recombination suppressed between the X and the Y? Well, it turns out the Y underwent a series of inversions, just like the one shown here. You'll see a few more. And as a result of the inversion, the X and the Y can no longer nicely align. And if they can't swap parts, what's going to happen? The fruits and veggies on the Y rot. The ultimate form of rotting is just plain getting lost and deleted. So the Y is going to get shorter. And now recombination is restricted to these regions that are still nicely aligned, nicely paired out at the ends. All right, we're going to zoom back to our timeline. We're now going to cross the point where we part company with the duck-billed platypus. And we're going to have some of the same themes. We're going to have some of the same themes reappear. We're going to have this Y undergo an inversion, which is a sort of an internal recombination event. Its ability to pair with the X is again reduced. Now, why isn't the X rotting? The X isn't rotting because two X's can still recombine in female meiosis. So genes on the X remain healthy because of ongoing recombination on the female side, whereas the Y is rotting because it's only being passed through a clonal line of males. Let the tape roll. Oh, some more rotting. This is just, cover your eyes if you can't stand the sight of it. Right. It's very hard for somebody who works on the Y chromosome to actually see this because it could very well be continuing to this day. Okay, now we're going to pass the point where we part company with the kangaroo. And now something interesting is going to happen. Another autosome is going to contribute a fresh supply of genes to both the X and the Y. This kind of renews the game, starts the game rolling again. But look, the Y just did another inversion, even within some of this newly acquired autosomal DNA. So guess what's going to happen? More rotting fruits and veggies. This is still, I mean, it's probably not happening in too many of the men in the room right now, but XY recombination still continuing just out at the ends. I think we're going to be desperately in need of some new kind of theme here. Unfortunately, as we move now down into primate evolution, well, we're not quite there yet. More shrinking. Really, really a tough time. The whole last 300 million years has been quite tough. Now we're getting down into primate evolution. And some good stuff is going to happen, guys. It's okay. Now, this other autosome, the permission of the X chromosome. Let's let the tape roll. So we're going to see a copy, as the tape rolls, we'll see a copy of the Dazzle gene insert into the Y, where it's now called Daz. And an amazing thing happens. The gene gets duplicated on the Y chromosome. And then those two get duplicated again. So we end up with 4 copies of Daz. It turns out the spermatogenesis genes on the Y, now fortunately none of this red stuff got lost. The spermatogenesis genes on the Y, in many cases, arose through this process of migration from autosomes. And so there we are. We got the sex-determining gene, SRY, one of these surviving housekeepers, RPS4Y, and spermatogenesis Daz. That gives us the modern human X and Y chromosomes, of course, in the context of the genome.